This is the third mechanics problem from the 1994 AP Physics C test. It depicts the Earth with a satellite of mass lowercase m in an elliptical orbit and focuses explicitly on the orbiting object, orbiting satellite, when it's at positions A and B, and it gives you some information about it, telling you that position A is a distance A, lowercase a from the center of the Earth, and position capital B is a distance lowercase b from the center of the Earth. Remember that the Earth center would be at one of the two foci. And we're told we have to solve the problems in terms of the variables that are given, where capital M sub e is the mass of the Earth. Lowercase v sub 0 is the velocity of the satellite when it's at position A. We can use distance A, distance B, the mass of the satellite, the mass of the Earth, the radius of the Earth, the velocity at position A, and the universal gravitational constant in our answers. In this year, in the third part of the question, in part C, you were asked to find the velocity at position B. Remember that you had been given the velocity at A as v naught. That was a lowercase v. You were given that the radial distance the satellite would be from the center of the Earth when it's at position A is lowercase a, and when it's at position B, the distance away would be lowercase b. An orbiting satellite conserves both mechanical energy, that's the combination of gravitational potential energy, and kinetic energy, but it also conserves angular momentum. So we have two ways to do this problem. And initially it might seem like one way is just as good as the other way. So we could justify that since the net torque that acts on the orbiting satellite is 0, though there is a gravitational force between the satellite and the Earth, that gravitational force always acts along the radial line vector, and so that gravitational force never creates a torque. Since the net torque is 0, the angular momentum of the orbiting satellite at any initial spot would be equal to the angular momentum of the orbiting satellite at any later position. However, since the work done by external forces, that would be like friction, drag, thrust, lift, normal force, since that is 0, we can also state that the gravitational potential energy at one spot plus the kinetic energy at that same spot will equal the gravitational potential energy at a later spot plus the kinetic energy at that later spot. In the first part of this test problem, they had you derive the formula for gravitational potential energy. In the second part of the problem, they had you compute the angular momentum of the orbiting satellite. So it might have seemed like they were giving the option of doing it both ways, but I'm going to show you why one of these two solutions is significantly better than the other one. So the angular momentum of a particle is equal to r cross p. So I'm going to state that the initial angular momentum is r naught cross p naught, and that'll have to be equal to r at a later point cross the p at a later point. If I was going to use this equation, I would say that negative g times mm, those are the two masses, over r plus 1/2 mv squared, I need an O there, I need an O there, that'll be equal to negative g mm over r, it's rf, plus 1/2 mvf squared. So it's looking like either one is doable, although this is already looking more complicated. Well, the radial distance vector to position A, the initial position, is given as A. And when you take r cross p, it's r mv sine phi. A is the r, m is the mass of the satellite, and the r m v is v naught. And then I would take the sine of the angle between the radius vector and the velocity vector, and that happens to be 90 degrees when the particle is at position A. The velocity would be tangent to the ellipse. The radius would point straight out to position A, so that's why the angle between the radius vector, the velocity vector is 90 degrees. When you get over to position B, you have the exact same angle, but it's going to be B times M times VB that we don't know, times the sine of 90 degrees. You can see that if we could divide both sides by mass, that would disappear. Sine of 90 is 1. So we simply have A V naught equals B times the velocity at B. We wanted to solve for the velocity when it got to position B. So the answer would be quite simple. A V naught over B is the velocity when the object is at position B. Quite simple. If we tried to achieve the same answer with conservation of mechanical energy, we would substitute in A for the initial radial distance, V naught, which basically is already substituted in, is the initial velocity. B is the final radial distance, and VB squared is what we want to try to solve for. Well, you can cancel the masses here, but you still end up with an equation that's really quite complicated and going to be difficult to rearrange and get into the variables that were in the list here that can be in the answer. You can see I've got the mass of the Earth, I've got A, I've got the mass of the satellite still, which I can cancel, I've got B, and so if we solve this for VB, it would be a much more complicated answer, and in fact would need to be rearranged until it was solved this easily. So the likelihood of earning full points is significantly reduced by using conservation of energy. Although it can still be achieved, it's much more complicated. So having more than one way to approach a problem can be advantageous. One way takes less time to compute, ends up being a much simpler answer. If this problem had numerical values for the velocity of the object at position A and the radial distance from the Earth to A and the radial distance from the Earth to B, we could plug them in at this point and compute an actual velocity. So hopefully you can see that for an orbiting satellite, angular momentum and mechanical energy are conserved, but often using the conservation of angular momentum can lead you to the simplest answer in the least time.